Hi kids, Mr. Dorfler here with another video on Intro to Chem Phys. Today we're going to be talking about Chapter 13 and we are finishing off Section 1 of that chapter. So far we've discussed work and power, okay? Every day you do work at various amounts of power, okay? So there are going to be times and plenty of instances where we aren't enough. And so we need to have assistance when we do work. And we need to do that work at various amounts of power and various amounts of time, therefore. So we are going to be talking about a term called mechanical advantage. Now, before we get into the notes today, I just want to say that your homework assignment this evening will be due tonight by 11:59. That way, everybody has it turned in, completed, and we can discuss it tomorrow in class. So make sure you pay attention to the due date and time, which is tonight at 11:59 p.m. All right. So we often use machines to help make our lives easier. A lot of you come to school either on the bus or through a car. Those are machines. But there are also a lot more simple machines that you might utilize more often than a complex machine like a vehicle. So eventually we're going to talk about those types of simple machines in the next section. But for now, we need to figure out how machines make our lives easier. And so machines help us do work by changing the size of an input force, the direction of the force, or both. So when we say input force, we mean how much do we personally have to put into a machine to help do a larger job, okay? So here's how they can do that. They can change the input force by redistributing the work that we put into them or changing the direction of an input force. Good example that hopefully you won't have to use, but it's a skill that everybody should know, especially for you young drivers, is how to use a car jack. Okay, car jacks are used to lift up cars, and they work by making the work easier by allowing you to apply less force at any given moment. And the jack requires the same amount of work to be inputted as lifting the car by hand would. So it's going to make your life a lot easier. Now, I learned the benefit and value of a car jack and how useful they are actually earlier this year in February. Very, very cold February that we had. I was driving my daughters and my wife to St. Louis for one of my daughter's volleyball tournaments. And we decided to have a flat tire on the side of I-55 at just after 6 o'clock in the morning. That was not a very fun way to start the day, laying next to a very busy interstate that early in the morning in wintertime. And here's a tip for all of you new drivers. In your car, no matter what vehicle you're going to be driving, always locate the jack in your car. Almost every single car comes with a car jack for these exact reasons. If you don't know where yours is, go look for it, because it'd be a great idea to know where it is and to make sure you actually have one. If you have a used car, it may have been taken out by somebody at some time. So you don't want to find yourself in a predicament where you don't know where your car jack is, and then when you finally find it, it is not there. So please make sure you can locate your jack in a situation to where you might need it, okay? So machines can also make the force greater by decreasing the distance over which the force is applied. So again, going back to the jack here, a jack makes lifting a car easy by multiplying the input force, and the structure of that jack allows the user to apply less force at any given moment. So you apply less force, it multiplies the force, and you're going a shorter distance, and eventually the car will begin to raise up. And so each machine, whether it be simple or complex, is going to have what we call a mechanical advantage, okay? It's a quantity that expresses how much machine multiplies force or distance. So it's just a ratio between the output force and input force. It's also equal to the ratio of the input distance and output distance, okay, as long as we ignore friction, which, we can't ignore friction. It's everywhere. Anyway, this formula for solving mechanical advantage might seem a little wonky, a little confusing. And that's because how I interpret this formula is the fact that there are actually two formulas. Okay, so what I recommend you do at this point is go ahead and write these two formulas down. I'm simplifying this. Okay, I'm simplifying this equation. So I'm going to go ahead and get into my camera here, possibly. Okay, so if we look at the formulas here, so mechanical advantage. First formula. Let me dim this a little bit. First formula, again, mechanical advantage is equal to the output force divided by the input force. Okay? So that's the first type of formula that we're going to be using. If I can get this camera straight. There we go. That's kind of straight. So that's one version of the formula. There's also the second where we look at the input distance, okay? And so mechanical advantage is equal to the input distance divided by the output distance. Okay, sorry for the chicken scratch. So I'll go over this again so you can write it in your own. Mechanical advantage, MA, is equal to output force divided by input force. You can also interpret it as mechanical advantage is equal to input distance divided by output distance. Okay, so when you are looking at problems regarding mechanical advantage, you need to see what they are providing you. Are they providing us forces or are they providing us distances? That's going to determine which one of these versions of the formula you're going to use. Okay? Oops, I need to brighten me up a little bit here. Okay. Let's get back into this now. Okay, so since we are dealing with a ratio, which is what mechanical advantage really is, there is no unit. Okay, there's no foot or newtons or anything like that. It's simply just a value, a number value. And so the number value is going to tell us what the mechanical advantage is going to be with a particular machine. So down here, number 4, how do we interpret mechanical advantage? If mechanical advantage is greater than 1, that means it's going to multiply the input force. Okay, so when we're talking about forces, if it's greater than 1, we're going to get more out of what we put in. This type of object could help you move a heavy object. This type of machine could help you move a heavy object. If we have a mechanical advantage less than 1, it's going to increase distance and speed, and it's going to require the amount of force required to. It's going to reduce the amount of force required to move an object. Okay. So we'll watch that video when we get back into it. All right. Now I'm going to skip the problem. I'm going to come back to the problem here in just a second because I want to finish the notes and then go back. So we also have ramps. Okay. If you've never moved anybody, then you're missing out on some great fun. Let me tell you. But oftentimes when you have a moving van and you're in charge of moving somebody, a lot of the moving vans like U-Hauls and everything like that are going to have a ramp that pulls out of the back and locks into place. That ramp is going to help you move heavier objects with greater ease. There is a take back from that though. It's going to require less force from you, but it's going to increase the distance over which you're going to apply that force. And the cool thing is, whether you use the ramp or not, you're going to be putting in the same amount of work. It just with the ramp, it's going to reduce the amount of stress you're going to be putting on yourself by lifting heavy objects. So, for instance, if we try to move a box that is straight up from the ground all the way back into the truck, if you have to use a force of 225 newtons on a box, and you have to move that box 1 meter directly up, okay, into the back of a van. See, I think you should be able to see the image here. Yes, right here, the bottom right picture. Again, you lift that box straight up about a meter, requires 225 newtons of force to do so, 1 meter. Well, we can see that the amount of work that was done, again, it's work because we moved an object a certain distance. Work equals force times time. 225 is the force times the 1 meter. You get a total work amount of 225 joules. Now, we use a ramp. I mentioned that it's going to reduce the amount of force that is going to be required of you to move it. So hopefully it saves your back. If you're an old person like me, it's going to save your back in the long run. So you're still going to need the same amount of force to move that box because that box weighs the same amount, 225 newtons. However, you are now going to move that box up a ramp that is 3 meters in length. Okay? So you're moving that box 3 meters in length, and it only requires you to use 75 newtons of input force. Okay, so that's a significant reduction of force compared to the first one. First one required you 225 newtons of force to lift it straight up. Here, you only need to put 75 newtons of force to move that box. But you are going to be moving it 3 meters. So again, if we calculate work done, we have 75 newtons of our input force multiplied by 3 meters of the distance that you moved it, you still have 225 joules of work done. So you are still going to be using the same amount of work overall, but less force will be required from you when using a ramp. So if you ever do help somebody move, I highly recommend you using a ramp, especially when you get older. Let's get back to our problem at hand. If I can, there we go. All right, so Alex, you might want to have a calculator out for this one, because what I recommend you doing is, once we get this all set up, pausing the video, calculating it yourself, and then checking your answer. Excuse me, I dropped my marker. Checking your answer with mine. So Alex pulls on a handle of a claw hammer. If you don't know what a claw hammer is, it's simply a regular hammer. Okay, it's got a claw on it with a force of 15 newtons. If the hammer has a mechanical advantage of 5.2, how much force is exerted on the nail in the claw? All right, getting back to this here. So let's first analyze what the question is asking us. Okay, so getting back into it, it says Alex pulls on the handle of a claw hammer with a force of 15 newtons. Okay, so we are dealing with a situation that is involving forces, not distances. So that's going to determine which formula we're going to use. Okay, and so if we go back to the formulas, since we're dealing with forces, we're going to be using the formula of mechanical advantage is equal to output force divided by input force. Okay, so mechanical advantage is equal to output force. I'm just going to call it OF to save some space, divided by input force. Okay, going back into here. Oops, I went too far. All right, so now we have to figure out what we know. Okay, Alex pulls on the handle of the claw hammer with a force of 15 newtons. That is the input force. That is the amount of force that Alex is putting in to the hammer, the simple machine. Okay, 15 newtons. Okay, I'm just writing down what we are given. It says the hammer has a mechanical advantage of 5.2. Again, you notice there's no units on there. So mechanical advantage equals 5.2. We need to figure out how much force is exerted onto the nail in the claw. So we need to figure out how much output force the hammer is having on the nail. So we don't know yet. So after we've listed what we know, we need to go back to the formula and rearrange it. Again, I'm the person who likes to rearrange it before I put any numbers in. If you like to put the numbers in, then rearrange it, perfectly fine. Okay, perfectly fine. But what we are trying to solve for is input force. So in order to get output force by itself, I'm going to multiply both sides by the input force. Okay, that'll cancel those out. And I'm going to get a formula that's going to now look like the output force is equal to mechanical advantage times input force. And now I can go ahead and plug in my numbers. Mechanical advantage is 5.2 multiplied by my input force of 15 newtons. Okay. And this is a moment where you want to pause the video. Or if you already paused it and try to figure out from the very beginning, cool. But here's where you want to pause the video. So to solve this, I'm going to go ahead and take my 5.2, multiply it by 15, and I'm going to get an output force of 78 newtons. Now remember, this Newton unit is going to come right down there. Okay, we're dealing with forces, so we have to have a unit of newtons on there. And that is our answer. So by simply putting in 15 newtons of force, which isn't that much really, we get out of that hammer 78 newtons. That's a pretty significant mechanical advantage, if I do say so myself. That's why they're used so often when removing nails from walls or anything else. So that actually wraps up section 1. Now, as a reminder, I said in the very beginning of the video that your homework, I think it's going to be 5 questions. It'll be due this evening, so make sure you do that video and make sure you complete all of your notes so that when we come back into class, hopefully tomorrow, we can continue on with our notes. So with that being said, if you have any questions, please feel free to contact myself or even Mr. Hampton, and we'll be seeing you later on. Have a good day, folks.